Hello there, and welcome to sleepy ancient Earth. Tonight, we drift back to the very beginning of the story, to a world so old it barely resembles our own. The Archean, the dawn of Earth. The Archean is not quite the molten world that came before it, not quite the living world that came after, but something in between. A planet cooling into its first solid ground. A sky without the blue we know. Some skies glowed a hazy orange-brown, tinted by drifting methane. Some seas held so much dissolved iron that they shimmered faintly green. Some days lasted only 21 hours, spinning beneath a moon far closer than ours, while a few patches of solid crust, no larger than islands, marked the only ground on an entire ocean world. If you enjoy these quiet journeys into the deep past, feel free to like and subscribe or share a thought in the comments below. It helps others find their way here too, one sleepy soul at a time. But for now, let this ancient green ocean carry you, and if you're ready, let's begin. The Archean Eon began about 4 billion and 3 million years ago. Geologists mark this moment as the start of Earth's readable history, the point where the planet stops being reconstructed from theory alone and starts leaving behind stone we can actually hold. The boundary is dated using zircon crystals pulled from the Acasta gneiss in northern Canada, grains of rock old enough to have watched the very start of this eon. The line itself is not a sudden event, but a convention, a place where geologists chose to draw a mark across a slow and continuous cooling. Still, it matters, because after this point, Earth had a surface stable enough to hold a record of itself. A single human life spans perhaps 80 years. The Archean spans 50 million such lifetimes laid end to end, and this was only its very first breath. Somewhere beneath a sky that had not yet found its blue, a planet was quietly beginning to keep its own diary in rock. That diary starts here. It followed the Hadean and lasted nearly 1.5 billion years. The Hadean had been an age of impact and molten rock, a world still remembering its own violent birth. And the Archean was what came after that fire finally settled. Its span runs from about 4 billion years ago to roughly 2.5 billion years ago, nearly a third of the planet's entire age contained within one eon. It was not a single unchanging stretch of time. Within it, the first oceans gathered, the first crust hardened, and somewhere near its middle, the first living cells appeared. Compare this to the eon we live in now, the Cenozoic, which has lasted a mere 66 million years, a fraction of the Archean's length. To stand at its beginning and its end would be to see two almost unrecognizable planets, joined only by the slow thread of geological time. An eon, it turns out, can hold entire biographies of a world within it. The name comes from a Greek word meaning beginning or origin. Geologists borrowed archaeos, an old word for ancient or primal. When they needed a name for the earliest span of Earth's history, they could still study with rock in hand. At the time this name was chosen, no one had yet found evidence of anything older, so the Archean seemed to mark true beginning itself. Later, geologists identified the Hadean before it, an even older interval named for the underworld, but by then the Archean had already kept its name. It stands now as a reminder that our labels for deep time are drawn as much from what we know as from what came before it. In everyday language, a beginning is a single moment. Here, it names 1.5 billion years of one. The word suggests a moment. What it actually holds is an age. Earth's crust had cooled enough to form permanent, if fragile, solid ground. Before this point, any crust that formed simply melted back into the mantle within a few million years, leaving no lasting record behind. Now, in scattered patches, such as the Isua Greenstone Belt in western Greenland, rock survived long enough to become part of the geological archive we still read today. This ground was thin and unstable compared to modern continents, prone to buckling and sinking back into the molten layers beneath it at the slightest provocation. Even so, its survival mattered enormously, because solid ground gave minerals a place to weather, oceans a shoreline to meet, and chemistry a stage on which to slowly experiment. Today's continents feel permanent beneath our feet, immovable and certain. The first ones were closer to rafts, drifting on a restless sea of molten rock below. The ground did not yet know how to stay still. The sun remained about 20% fainter than it shines today. Young stars burn with less intensity than mature ones, and 4 billion years ago, the sun was still working its way toward the brightness it holds now, a brightness it would only reach many billions of years later. By simple physics, a fainter sun should have left Earth locked in ice, its oceans frozen solid under a dim and distant light. Yet the rock record shows liquid water pooling and flowing across the Archean surface, a puzzle scientists call the faint young sun paradox. Something else in the young Earth's atmosphere must have been holding on to heat that sunlight alone could not provide. This mismatch between a cool sun and a warm planet has never fully been resolved, and it remains one of the more curious open questions of this eon. The sun gave less. Somehow, the Earth still had enough. Despite this faint sun, the Archean climate stayed warm, even temperate. Studies of ancient ocean chemistry, preserved in ratios of oxygen isotopes locked into ancient rock, suggest surface waters may have sat somewhere between 26 and 35 degrees Celsius, closer to a warm bath than the cold seas one might expect from a dimmer sun. Glaciers were rare across most of this eon, appearing only in brief, scattered episodes, rather than the long ice ages that would follow in later periods of Earth's history. This steady warmth meant the oceans stayed liquid nearly without interruption for well over 1 billion years, giving early chemical processes an unbroken stretch of time to work without the setback of a frozen world. A fainter sun might have promised only cold and stillness, and yet the Archean stayed mild instead, warmed by something other than sunlight alone. Ice would come later, in ages far more familiar to us. For now, the world simply stayed warm. High levels of carbon dioxide and methane trapped heat in the air, holding on to warmth that a faint young sun could not supply on its own. Volcanic activity across the Archean released carbon dioxide in enormous quantities, while newly evolved microbes exhaling methane as a byproduct of their metabolism added a second, even more powerful heat-trapping gas to the mix. Together, these gases may have made up several hundred times the concentration found in today's atmosphere, a chemical blanket thick enough to compensate for a dimmer star. This was not warming caused by industry or by any deliberate act, simply the natural exhale of a young planet in its earliest life, settling into balance with the light it received. Modern atmospheres hold far less of these same gases, kept in careful check by oceans, forests, and rock cycles working in concert. In the Archean, no such checks existed yet. The air simply held what the world gave it, and the world in turn stayed warm. Free oxygen was still essentially absent from the atmosphere. Across the early Archean world, the air held almost none of the gas that fills nearly a fifth of a modern breath. Estimates place free oxygen at less than 1,000,000% of what it is today, a trace so faint it left barely any mark on the rocks that recorded it. This was not a world without oxygen atoms, only a world where those atoms stayed bound into water and mineral, rather than drifting free as gas. Because of this, iron dissolved directly into the oceans, instead of rusting into solid form, leaving seas rich with metal in a way none are now. A person breathing this air would draw in nothing useful, no relief, only stillness where a lungful of oxygen should be. To stand on an Archean shoreline and breathe deeply would be to breathe almost nothing at all for a body built on later air. The air was full. The one gas we now depend on simply was not part of it. The sky likely appeared hazy, tinted orange-brown by methane photochemistry. High above the Archean surface, sunlight broke methane molecules apart and stitched the fragments back together into tiny organic particles. The same kind of haze that colors the skies of Saturn's largest moon today. Atmospheric models suggest this haze layer may have hung tens of kilometers up, thick enough to give the daytime sky a dull amber cast rather than the blue we know. This was not smoke or pollution in any human sense, simply chemistry working on gas warmed by starlight. The haze likely cooled the surface slightly, even as greenhouse gases below it warmed the air. A delicate balance between two effects pulling in opposite directions, where a modern sky scatters blue light through nitrogen and oxygen. The Archean sky filtered it instead through drifting organic particles. A sunrise here would break slowly through haze the color of weak tea. Its light softened long before it touched the water. Even the color of daylight, it seems, carries a history of its own. Without ozone, ultraviolet radiation still reached the surface largely unblocked. No layer of ozone yet wrapped the upper atmosphere, because ozone forms from oxygen, and oxygen was still barely present in the Archean air. Ultraviolet light likely struck the surface at levels several times higher than anything experienced on Earth today, unfiltered and constant across the exposed land and shallow water. This did not make the surface uninhabitable, only selective, favoring life that stayed submerged, sheltered in sediment, or protected by simple pigments that absorbed the harshest wavelengths before they could cause harm. Shallow seas likely served as a kind of shield, since even a few meters of water could soften radiation that would otherwise reach unguarded cells directly. Imagine standing on an Archean beach at midday, the light around you sharper and more penetrating than any sun a human has ever felt on their skin. Life found its way regardless, tucked into water and mud, waiting for a layer of ozone still hundreds of millions of years away. The surface was open, but never entirely welcoming. A day on Archean Earth lasted roughly 21 hours, not 24. Earth then spun faster on its axis than it does now, completing a full rotation in less time than it takes to watch two modern films back to back. Calculations based on the physics of tidal drag suggest this shorter day held steady across much of the Archean, with sunrise following sunset more quickly than any calendar we now keep. No creature existed yet to notice the difference, no eye to watch a sun that set sooner and rose again before a modern body would call it rest. The shorter day meant a faster rhythm to everything the planet did. Tides rising and falling more often, temperatures shifting through their cycle at a slightly quicker pace. Our own 24-hour day is simply the version this planet eventually settled into, stretched out gradually over billions of years of slowing spin. A 21-hour day would have felt unremarkable to anyone living inside it, since it was the only day they had ever known. Time itself was simply shorter then, and no one was there to mind. The moon orbited closer than today, raising larger, faster ocean tides. In the Archean, the moon sat tens of thousands of kilometers nearer to Earth than it does now. A difference built from billions of years of slow separation still underway. Because of this closeness, its gravitational pull acted more strongly on Earth's oceans, and tides likely rose and fell across greater heights than any tide a modern shoreline ever sees. These tides moved more often too, following the shorter Archean day, so that shallow coastal waters surged and retreated at a noticeably brisker pace. Such motion churned nutrients and minerals through shallow water again and again, stirring the very chemistry that early life depended on to survive. A modern beach might see 2 gentle tides a day. An Archean shore saw something closer to a heartbeat, tides rising with more force and less rest between them. The moon, hanging larger and brighter in that ancient sky, was quietly rearranging the chemistry of the ocean beneath it, one tide at a time. Earth's rotation was gradually slowing as tidal friction pulled at the moon. Each time the ocean tides rose and fell against the pull of the moon, a small amount of Earth's spinning energy transferred outward, pushing the moon a little farther away and slowing the planet's own rotation in return. The change was, and still is, remarkably small, adding only a few thousandths of a second to the length of a day across an entire century. Over the vast reach of the Archean, though, these tiny increments added up into real difference, stretching a 21-hour day slowly toward the 24-hour day taken for granted today. It is as though the Earth and Moon have spent billions of years trading momentum back and forth, one slowing as the other drifts farther away. No single Archean lifetime would have felt this shift happening. Only the accumulated weight of deep time reveals it at all. The ordinary day we now live inside was built this quietly, one unfelt tug at a time, long before anything existed to keep count. Volcanic activity was far more intense than at any later time. Earth's interior in the Archean still held enormous residual heat left over from its formation, along with heat generated by far more abundant radioactive decay than exists in the planet today. This heat needed to escape, and it did so through volcanism on a scale no later era would match. With eruptions releasing lava so hot, it flowed almost like water across the surface. Geologists identify traces of this in an ancient rock called komatiite, a lava type essentially absent from any eruption in the last few 100 million years, because the mantle no longer burns hot enough to produce it. This relentless volcanism built the earliest fragments of continental crust, while also releasing much of the carbon dioxide that kept the young planet warm beneath its fainter sun. Where modern volcanoes erupt in scattered occasional bursts, the Archean world seemed to simmer everywhere at once. The ground itself was still remembering its own birth, and it had not yet learned to be still. Heat flow from the mantle was several times greater than today's. Beneath the thin Archean crust, the planet's interior still carried heat from its violent birth, compounded by radioactive elements that decayed far more quickly then than they do now. Geologists estimate this heat flow reached 2 to 3 times modern levels, an intensity no longer found anywhere on the planet's surface. It did not simply linger beneath the crust. It pushed upward constantly, seeking any weakness through which to escape. Modern Earth cools quietly, its heat flow measured in careful whispers across continents that barely stir. The Archean world had no such patience. To stand on its surface would have been to feel warmth rising faintly, even through solid stone, a warmth no later era would ever match. That warmth explains almost everything else about this early world, from its restless volcanoes to its thin, unstable crust. Heat does not vanish. It moves outward, and it moves the world with it. This heat drove frequent eruptions of a lava called komatiite. Across the Archean world, this iron and magnesium-rich rock surfaced again and again, spilling from fissures with an ease that no lava manages today. Some flows stretched for many kilometers before cooling, moving with the loose fluidity of water rather than the slow crawl expected of molten rock. Fossilized flow patterns, preserved in ancient greenstone belts found today in Canada and Australia, still show the ripples left behind as komatiite spread and thinned across the young crust. Where a modern lava flow might advance at a walking pace before stalling, komatiite could outrun a person on foot. Its abundance says something startling about the planet beneath it. A mantle so hot that ordinary volcanic behavior simply did not apply. Each fissure that opened was a small reminder of how young and overheated the Earth still was. The rock itself remembers what the surface has long since forgotten. Komatiite erupted at temperatures far higher than any modern volcanic rock. Modern basalt, the most common lava on Earth today, typically emerges from the ground at close to 1,200 degrees Celsius. Komatiite ran hotter still, reaching estimates near 1,600 degrees, hot enough to glow nearly white before darkening as it cooled. This extra heat came from a mantle rich in magnesium, a mineral that raises the eruption temperature dramatically when melted in such abundance. Scientists reconstruct these temperatures indirectly by studying the crystal structures left behind in ancient komatiite samples, since no eruption remains to measure directly. At such heat, the lava's thickness dropped low enough to flow almost like heated syrup, rather than the slow, stiff paste of ordinary lava. No volcano alive today could produce a flow so hot or so fluid. The Archean mantle simply ran at a temperature the modern Earth has never returned to. No such lava has erupted anywhere on Earth for billions of years. The last widespread komatiite flows are found in rocks roughly 2 billion years old, marking a point after which this molten rock simply stopped appearing. As Earth's interior slowly cooled, radioactive decay tapered off, and the mantle lost the extreme heat needed to produce it. What remains today are only the frozen witnesses, thin bands of dark green and black rock preserved in a handful of ancient terrains, including sites in Zimbabwe and Western Australia. Geologists study these bands the way one might study a fossil, reading temperature and chemistry from stone rather than bone. One puzzling flow on a remote Pacific island erupted far more recently, though its origin is still debated and changes little about the general pattern. For nearly all of Earth's later history, this lava has simply had no way to exist. Some things do not return once the world that made them has cooled. Whether true plate tectonics operated in the Archean remains scientifically debated. Modern Earth's crust moves as rigid plates, sliding, colliding, and diving beneath one another in a slow global choreography that shapes mountains and oceans alike. It is unclear whether the thinner, hotter Archean crust was capable of this same rigid behavior, since intense heat tends to soften rock and blur the sharp boundaries that plate motion requires. Some evidence, drawn from ancient magnetic minerals and patterns preserved in old greenstone belts, hints that fragments of crust may have shifted and collided even then. Other evidence suggests a crust too soft and mobile to break into distinct plates at all. The debate has continued for decades without full resolution, and the rock record from 4 billion years ago is thin enough that certainty may never arrive. What is clear is that something moved this ancient crust, whether by the mechanism familiar today or by one no longer available to a cooler Earth. The ground was in motion. Only its manner remains uncertain. Some geologists propose a different, slower style of crustal movement instead. Rather than rigid plates sliding past one another, this model imagines a crust behaving more like a pot of thick porridge left too long on the heat, folding and overturning in place, rather than breaking into distinct pieces. Heavier volcanic rock, once cooled and thickened at the surface, could have grown dense enough to sink back into the softer mantle beneath it, a process researchers call dripping or sagging rather than subduction. Evidence for this idea comes partly from deformation patterns preserved in the Isua rocks of Greenland, among the oldest exposed stone on Earth. This sinking would have dragged surrounding crust downward with it, creating slow, circular currents instead of the linear boundaries seen in modern plate tectonics. Such motion would have been gentler and far less structured, without the sharp mountain ranges or deep trenches that define today's plate edges. Whichever version is closer to the truth, the crust was never a fixed and finished thing. It moved because it had to, however awkwardly it managed the motion. Small proto-continents called cratons began forming from cooling volcanic rock, as komatiite and other early lavas solidified and thickened over hundreds of millions of years. Patches of crust grew light and stable enough to resist sinking back into the mantle below. These patches, known as cratons, became the first durable pieces of land on Earth, ancient cores around which every later continent would eventually be built. Fragments of Archean craton still exist today, buried beneath younger rock in places such as the Pilbara region of Western Australia and the Kaapvaal region of South Africa. They were small by modern standards, often no larger than a present-day country, scattered like islands across a planet still mostly ocean. Unlike the shifting, short-lived crust around them, cratons proved remarkably resistant to erosion and remelting, preserving some of the oldest rock ever found. In them, the Archean world left its most patient signature, one that has survived every upheaval since. Continents did not begin as continents. They began this small and this quietly. The Pilbara Craton in Australia preserves some of the oldest known crust. Tucked into the northwest of the continent, it sits among the handful of places on Earth where Archean rock still reaches the surface rather than lying buried under younger layers. Some of its formations date back roughly 3.5 billion years, among the oldest stone ever measured. This is not untouched, original crust. It has been folded, heated, and partly rebuilt many times since it first solidified. Even so, it holds traces of a chemistry no younger rock preserves. Faint chemical signatures of an ocean, an atmosphere that no longer exist anywhere else. Most of Earth's early surface has long since been swallowed and remade by the planet's churning interior, but the Pilbara endured, thickened just enough to resist the pull below. This ground was already ancient when almost everything else on the planet was still forming. It is a small patch of permanence in a world that otherwise kept dissolving itself. The Kaapvaal Craton in southern Africa formed during this same span. Half a world away from the Pilbara, in what is now South Africa, another patch of crust was thickening and stabilizing along a similar timeline. Somewhere between 3.5 and 3 billion years ago. Its rocks differ in composition, richer in certain volcanic minerals, suggesting it grew from its own separate pocket of magma rather than sharing a single origin with its Australian counterpart. Geologists take this as a hint that crust building was not a single event, but a pattern, happening independently in more than one place as the planet slowly cooled. Together, the two cratons support the idea that solid land was becoming possible everywhere conditions allowed it, not by design, but by simple repetition of the same patient chemistry. Their rock records remain among the best surviving windows into that process. The Pilbara tells one version of that story, and the Kaapvaal tells another, written in slightly different stone. Two continents apart, born of the very same quiet process. These early land masses were likely small islands scattered across a vast ocean. Cratons like the Pilbara and the Kaapvaal did not join into anything resembling a continent, not yet. Each may have measured only a few hundred kilometers across, modest patches of solid ground rising just above a global sea that stretched, by some estimates, over most of the planet's surface. No towering peaks broke the water's surface, and no shoreline stretched further than a long day's walk. Between these scattered patches lay open water in every direction, uninterrupted by any continent as we would recognize one now. Whatever crust existed clung together in modest, imperfect shapes, still finding its footing chemically and physically against a mantle that kept trying to reclaim it. To stand on one of these islands would have meant standing at the edge of nearly everything, with water reaching toward every horizon. The land was real, but it was rare. Islands, not continents, were the shape the world had chosen for now. Continents as large as today's would not exist for billions more years. What passed for land in the Archean bore little resemblance to Asia or Africa or any of the great land masses familiar now. Cratons needed to collide, weld together, and accumulate volcanic material for eons before anything approaching continental scale could form, a process that would not begin in earnest until roughly 2 billion years ago. Even then, the assembly was gradual, interrupted, and often undone by the same tectonic forces that built it in the first place. This slow pace was not a failure of the planet, but simply the nature of building something so large from pieces so small. Every mountain range and coastline familiar today descends from this patient accumulation. To imagine the Archean surface is to picture a puzzle with only a handful of its pieces cut, laid out across a table, mostly bare. The rest of the picture was still being made. The global ocean may have covered far more of the surface than now. With continents still small and scattered, water had far less land to interrupt it, and by some estimates, oceans blanketed close to 90% of the planet's surface, compared with about 70% today. This was not a shallow film of water, but a deep, largely uninterrupted expanse, broken only by the occasional volcanic island or craton edge. Without large continents to divert them, ocean currents likely moved in patterns very different from the ones that circulate heat around the planet now. Rainfall, evaporation, and weather all unfolded across water rather than land, shaping a climate system with almost no parallel today. This was a world defined by sea in a way the modern Earth no longer is. Everywhere you might have looked, water reached toward the sky. It was less a planet with oceans than an ocean with a few scattered stones. Seawater likely held far more dissolved iron than modern oceans do. Today's oceans carry only trace amounts of dissolved iron, filtered out almost immediately by oxygen-rich water and the countless organisms that use it. The Archean Ocean lacked that filter, since free oxygen was still vanishingly rare in both air and sea. Without it, iron released by underwater volcanic vents and weathering rock could linger, dissolved and invisible, accumulating across millions of years rather than settling out quickly. Scientists infer this from banded iron formations, layered rock deposits found on several continents that record iron precipitating out of the water in vast quantities once conditions finally changed. These bands remain some of the clearest fingerprints of ancient ocean chemistry available anywhere. The sea, in this era, was as much a chemical reservoir as a body of water. It carried its history suspended within it, waiting patiently to be written into stone. This iron gave many Archean seas a faint greenish tint. Dissolved ferrous iron, the chemical form common before oxygen became abundant, imparts a pale green or grey-green cast to water when present in high concentration, unlike the clear or blue tones familiar today. Under a sky itself, likely hazy with volcanic gases, and lacking the ozone layer that scatters blue light so vividly now, the effect may have been subtle rather than vivid, a muted wash rather than a bright colour. No person stood on any shore to see it, so the description survives only through chemistry and inference, reconstructed rather than witnessed. Still, geologists find the image useful for imagining how differently the planet's surface might have appeared. Green seas beneath a grey sky would have looked like no coastline on Earth today. It was a planet dressed in colours it would later shed entirely. Ocean temperatures may have been warmer than today, though estimates vary widely. Reconstructing Archean climate means working backward from chemical traces left in rock, since no thermometer from that era survived to be read directly. Researchers rely on the ratio of oxygen isotopes preserved in ancient silica deposits, a method that shifts depending on assumptions about seawater composition at the time. Some readings point toward a hot planet, others towards something closer to modern conditions, and the gap between them remains wide. This matters because ocean temperature shapes everything from the pace of chemical reactions to the kinds of organisms able to survive within it. Compared to today's global ocean average of around 17 degrees Celsius, even the lower Archean estimates describe a noticeably warmer world. Standing at the edge of that ancient sea, the air itself might have felt heavy and close. The true number stays out of reach, held just beyond what stone is willing to say. Some studies suggest Archean seawater approached 55 degrees Celsius near the equator. This figure comes from measuring oxygen isotopes locked inside ancient cherts, fine-grained rocks formed from silica that settled slowly on the seafloor billions of years ago. If the calculations hold, equatorial waters in the Archean would have felt closer to a hot spring than an ocean, warm enough to feel uncomfortable against human skin within moments. Researchers are careful to note this estimate assumes seawater chemistry stayed fairly stable over enormous stretches of time, an assumption not everyone accepts. If accurate, such heat would have limited which chemical reactions could occur, and which forms of early life could tolerate the conditions. Modern tropical oceans rarely exceed 30 degrees Celsius, making this proposed Archean sea almost twice as intense by comparison. To imagine wading into water that warm is to imagine an ocean behaving less like a sea and more like a simmering pool. Whether the whole planet felt this way remains an open question. The rock offers a number, not a certainty. Other researchers argue the ocean stayed far cooler than that estimate. Using the same isotope methods, but different assumptions about ancient seawater chemistry, these studies calculate temperatures closer to 26 or 35 degrees Celsius, a range that overlaps comfortably with parts of today's tropical seas. The disagreement comes down to how much the isotopic ratios were altered by later geological events. Since rock that old has often been buried, heated, and reshaped many times over billions of years, both camps work from the same handful of ancient outcrops, yet arrive at strikingly different pictures of what the ocean actually felt like. This matters for understanding early life, since a merely warm sea allows for a far wider range of organisms than a scalding one. Modern oceans span a similar range depending on latitude, from icy poles to warm shallows near the equator. Perhaps the Archean Ocean held that same kind of variation. The record goes quiet here, leaving two plausible worlds standing side by side. Salt levels in the early ocean may have differed from today's seas. Geologists estimate ancient salinity by examining tiny pockets of trapped fluid preserved inside very old rock salt deposits, natural time capsules that occasionally survive from billions of years in the past. Some of these inclusions suggest Archean seawater may have carried noticeably different concentrations of dissolved salts than modern oceans, shaped by a planet still settling into its long-term chemical balance. Volcanic activity, still intense and widespread, constantly added new minerals to the water, while the biological processes that regulate salinity today had not yet evolved. A different salt balance would have affected water density, ocean circulation, and which chemical reactions could proceed easily near the surface. Today's oceans average a salinity of about 3.5%, a figure shaped over eons by biology as much as geology. The Archean Sea followed no such steady hand. It simply reflected the raw chemistry of a much younger Earth. Rain falling through a methane-rich sky may have looked faintly orange. Atmospheric models suggest that during parts of the Archean, methane accumulated in far greater quantities than in the modern air, produced by early microbial life before oxygen became common enough to break it down quickly. At sufficient concentrations, methane scatters sunlight in a way that can tint the sky and any haze within it towards soft oranges and browns, an effect seen today in the thick atmosphere of Saturn's moon Titan. If Earth's early sky held a similar tint, then rainfall passing through it may have carried that same warm coloring on its way to the ground. No one stood beneath that sky to describe it, so the image comes entirely from chemistry rather than memory. Today's rain falls through a sky kept blue by oxygen and ozone, scattering light in a completely different way. The Archean sky answered to different rules. Its rain fell the color of a sky that no longer exists. Without significant land plants, rivers ran unchecked across bare volcanic ground. No roots existed yet to hold soil in place or slow the movement of water across the land, since plants would not colonize continents for billions of years still to come. Instead, rivers spread wide and shallow, braiding into many shifting channels that moved freely across loose volcanic sediment with each new rainfall or flood. Geologists identify these ancient braided patterns in preserved rock layers, distinct from the single winding channels rivers tend to carve where vegetation holds their banks firm. Without plants to slow erosion, sediment traveled quickly from highland to sea, reshaping the land's surface at a pace unfamiliar to any river system today. Modern rivers, threaded through forests and grasslands, behave far more predictably by comparison. Their courses stabilized by unseen networks of roots. Archean rivers followed no such restraint. They moved as the bare land allowed them to move, and nothing held them back. Erosion patterns from this era differ sharply from anything seen since. Geologists studying Archean rock formations find wide, sheet-like deposits of sediment rather than the narrow, meandering patterns typical of river systems shaped by vegetation. This difference reflects a fundamental change in how land behaved before plants existed to anchor soil and slow the flow of water across exposed ground. Without root systems to intervene, rainfall and rivers carried sediment away almost as quickly as it formed, spreading it broadly rather than channeling it into defined paths. Some researchers interpret these patterns as evidence of a land surface in near constant motion, reshaped by every storm rather than settling into long-term stability. Since the rise of plants roughly 400 million years ago, nearly every landscape on Earth has been shaped by their steadying influence. The Archean world knew no such steadiness. Its ground shifted freely, and the rock still remembers exactly how restless it once was. Meteorite impacts continued, though far less frequently than in the Hadean. By the mid-Archean, the solar system had cleared much of the debris left over from planet formation, and Earth no longer faced the constant bombardment of its youth. Impacts still occurred, scattered across tens of millions of years rather than every few centuries. The difference mattered enormously for whatever life existed on the surface or in the shallows. A calmer sky meant longer stretches of undisturbed time, periods in which chemistry could settle into something more permanent without being erased. Where the Hadean offered no such patience, the Archean began, slowly, to grant it. Consider a single, quiet interval, one lasting 100 million years, in which nothing large enough to matter fell from above. That kind of stillness allowed fragile arrangements of molecules to persist long enough to become something else. The sky was clearing, and life, wherever it had begun, was finally being given room to continue. A large impact may have struck Earth around 3.2 billion years ago. By this point in the Archean, the planet had grown quieter, its surface settling into slow, deliberate rhythms of rock and water. But the solar system had not yet finished shedding its old debris entirely, and one last giant strike appears to have interrupted that calm. The object responsible may have measured many kilometers across, large enough to leave a mark still visible in the geological record billions of years later. Its scale dwarfs anything humanity has ever recorded striking the planet. Where a modern impact of even modest size would dominate headlines for a generation, this one left evidence buried so deep it went unnoticed until scientists learned where to look. Picture a stone the size of a small mountain, falling from a grey sky into a grey ocean, sending shockwaves through water that had never known such violence. The world absorbed it, as it always did, and simply carried on. Evidence for this impact comes from spheral layers found in South Africa. These layers consist of tiny, rounded droplets of rock, formed when material vaporized by the impact cooled and fell back to Earth as fine debris. Geologists have traced them within the Barberton Greenstone Belt, one of the oldest and best preserved fragments of Archean crust known anywhere on the planet. The spherules themselves are smaller than grains of rice, yet each one preserves a record of an event violent enough to melt stone into vapor. Fossils can only tell us so much from this era, and here there are no fossils at all, only these tiny beads of altered rock scattered through ancient sediment. Nothing else on Earth's surface survived from that single afternoon, if afternoon is even the right word for a day 3 billion years gone. Within a layer no thicker than a hand's width lies the only remaining trace of a mountain falling from the sky. Such impacts could have boiled parts of the ocean's surface temporarily. The energy released by a large enough strike would have vaporized seawater across a wide area, sending scalding steam and debris into the atmosphere within moments of contact. Local temperatures may have spiked high enough to sterilize shallow waters for miles around the impact site, at least for a short while. Yet the ocean as a whole was far too vast for any single strike to boil away entirely, and its deeper waters would have remained undisturbed throughout. Heat like this rises and dissipates quickly against a planet-sized body of water, the way a match flares and dies against a night sky it cannot touch. Somewhere beyond the reach of the steam, life in cooler waters simply continued, untouched by catastrophe. The ocean absorbed the wound and closed back over it within centuries, leaving barely a scar behind. Despite these disruptions, life had already taken hold on the young planet. Whatever chemistry first crossed the threshold into something we might call living had done so before this impact, and perhaps long before it. That head start proved decisive. A world with no life to protect could be sterilized and simply remain empty. But a world already carrying living systems in scattered refuges had a way of enduring even violent interruption. Deep vents, quiet lagoons, and undisturbed pockets of ocean floor likely held populations far from any single point of catastrophe. Modern volcanic disasters can devastate a region for decades, yet life elsewhere on the planet continues without pause. The Archean followed the same quiet logic, only stretched across far greater stretches of time and far greater degrees of violence. Life did not need the whole world to be safe. It only needed somewhere, and it had already found that somewhere long before the sky fell again. The oldest widely accepted evidence for life dates to this eon. Structures called stromatolites, layered mounds built by ancient microbial mats, appear in rock formations across Western Australia, dated to roughly 3.5 billion years old. These are not the bones or shells of any recognizable creature, but the fossilized architecture of communities, colonies of organisms that trapped sediment and minerals as they grew, layer upon layer, toward the sunlit water above them. What seems like plain banded rock is actually a record of billions of small, patient lives, each one working without awareness toward a structure none of them could see completed. The mats that built these formations still exist today in a few isolated lagoons, largely unchanged in form after 3.5 billion years. To look at a stromatolite is to look at one of the longest-running processes life has ever sustained. It has barely needed to change at all. Microscopic organisms called prokaryotes were the only life that existed. These simple cells lacked a nucleus or any of the complex internal structures found in plants, animals, or fungi today, relying instead on a single loop of genetic material floating freely within the cell. Two broad groups made up this early world: bacteria and archaea, distinguished by subtle differences in their chemistry rather than anything visible to the eye. For well over 1 billion years, nothing more complicated than this would exist on Earth in any form. No creature moved with purpose. No creature could see or eat or flee. There was only division, endless and patient. Cell becoming 2 cells becoming 4, spreading slowly through oceans that stretched further than any shoreline yet in existence. It was the simplest possible beginning, repeated without end. Everything that would ever live afterward, every root and wing and thought, descended from something no larger than a single drifting speck. These simple cells had no nucleus and no internal compartments. Inside an Archean microbe, there were none of the small working rooms that define life today. No mitochondria to burn fuel. No separate chamber to house the genetic code. Everything moved freely within a single membrane, a single open space where chemistry happened without walls. This was not a deficiency so much as an early solution, spare and efficient. It let these organisms divide quickly, react to their surroundings without delay, and pass changes to the next generation almost as soon as they appeared. A human cell, by comparison, is a small city of specialized parts, each with its own function and its own boundary. An Archean cell was closer to a single room, holding everything at once. To imagine one is to imagine life stripped down to its barest working parts. Nothing hidden, nothing divided. Simplicity, in this case, was not a limitation. It was the entire strategy. All Archean life was single-celled, invisible without modern instruments. No eye, then, or for billions of years afterward, could have found it. A single drop of Archean seawater likely held thousands of these microbes, drifting and dividing in numbers too small to see and too vast to count. None of this activity would have been visible from shore, if shore had meant anything at that point, and none of it left any mark a passing observer could have noticed. Yet these invisible cells were already changing the planet's chemistry, one reaction at a time, shaping the air and the rock in ways that would matter long after they were gone. If you could shrink to the scale of one of these cells, the ocean would feel less like water and more like a crowded field, thick with drifting shapes as far as any cell could sense. Such water, ordinary and still on its surface, was impossibly busy underneath. The smallest life on Earth was, for a very long time, the only life there was. Some organisms likely resembled modern bacteria and archaea in basic form. Under a microscope, the earliest cells probably appeared as simple rods, spheres, and gentle spirals, shapes still common among bacteria today. Most measured only a few micrometers across, far smaller than the width of a human hair, yet each carried everything needed to survive, feed, and divide. These forms were not accidents. They were efficient solutions to the basic problems every cell faces: how to hold together, how to move, how to take in what it needs from the water around it. Some of their descendants persist almost unchanged in hot springs, salt flats, and deep sea vents, environments harsh enough to have discouraged much further change. Placed side by side, an Archean cell and one of these modern survivors might be difficult to tell apart under a simple lens. Shape, it turns out, can be one of life's most conservative inventions. Some solutions, once found, are never really improved upon. Scientists believe archaea and bacteria had already diverged as separate lineages. The split may be one of the oldest divisions in the story of life, predating almost everything else that would follow. Genetic comparisons among living organisms suggest this branching point lies deep in the Archean, long before either group left any fossil distinct enough to mark the moment. The two lineages share a common ancestor, but differ in the chemistry of their cell membranes and in the machinery they use to read their own genetic code. Neither branch is older or more advanced than the other. They are simply different answers to the same ancient problem of staying alive. Bacteria would go on to fill nearly every environment on Earth, while archaea would often persist in its most extreme corners: salt lakes, boiling springs, oxygen-starved mud. The fork in that tree happened silently, without witness. In oceans no one would ever see. Two paths opened, where before there had been only one. Life may have relied on chemosynthesis, drawing energy from mineral reactions. Long before sunlight became a usable source of energy, the earliest organisms likely built their chemistry around reactions between simple inorganic compounds, combining hydrogen with carbon dioxide, or oxidizing iron and sulfur drawn from rock and water. No light was required for any of this. The chemistry alone provided enough energy to hold a cell together and let it divide. This mattered enormously, because it meant life did not depend on the sun at all in its earliest years, and could exist in total darkness, deep within rock, sediment, or the crushing black of the deep ocean floor. Imagine an entire biosphere running on the same kind of chemistry that rusts iron or sours a hot spring, patient and slow, needing nothing from the sky above. Most life today still depends, directly or indirectly, on sunlight passed along through plants. The very first life needed only rock, water, and time. Hydrothermal vents on the seafloor may have hosted some of the earliest communities. Along cracks in the ocean crust, mineral-rich water heated by the planet's interior poured out into the cold sea, carrying with it hydrogen, sulfur, and metals dissolved from deep within the rock. Modern vents of this kind still exist, some reaching several hundred degrees Celsius at their core before cooling rapidly in the surrounding water, and they still host dense communities of microbes found nowhere else. In the Archean, before the surface world had settled into anything stable, these vents may have offered rare, dependable conditions: warmth, chemical energy, and shelter from a sky still crossed by falling debris. If you stood beside one today, wrapped against the heat and pressure, you would find clouds of mineral particles billowing upward, like slow, underwater smoke. It is one of the few environments on Earth that may have remained remarkably similar across 4 billion years. The deep sea kept a version of the beginning alive. Methanogens, organisms that produce methane, likely thrived in these environments. These microbes take in hydrogen and carbon dioxide and release methane as a byproduct. A simple exchange, that asks little from their surroundings and returns a gas that would go on to shape the entire planet. In the Archean, before oxygen had accumulated in any significant amount, methanogens may have been common across the seafloor and in shallow waters alike, quietly producing gas by the billions of tiny reactions each day. That methane rose into the atmosphere and helped trap heat from a sun that, at the time, burned about 30% fainter than it does now. Without this warming effect, the oceans might have frozen solid, despite every other condition being right for life. The atmosphere above an Archean sea would have carried a faint haze, unfamiliar and thick, nothing like the clear blue sky above it today. A single, unremarkable microbial habit may have kept an entire planet from freezing over. Their waste gas, methane, helped warm the planet despite the dim sun. In the early Archean, the sun's output fell short of what a stable ocean would seem to need, and something had to close the gap. Methane, released by microbes scattered across the seafloor, may have reached concentrations hundreds of times higher than the trace amounts drifting through our air today. The microbes were not solving a problem. They were simply feeding. And the warmth that followed was an accident of their hunger. Yet that accident kept the ocean liquid through an age when the numbers alone predicted ice from pole to pole. Today, we think of methane mainly as a pollutant, a gas to be measured and reduced. But in the Archean, it worked closer to a lifeline than a threat. Picture the sky then, pale and close, holding in a warmth it had no obvious right to hold. The planet survived by accident, and the accident kept happening for 1 billion years. Sulfur-based chemistry also sustained certain early microbial communities. Not every organism in the Archean seas relied on hydrogen and carbon dioxide the way the methanogens did. Some instead drew energy from sulfur compounds, dissolved into the water from volcanic vents and weathering rock, using them much as later life would use oxygen to release energy from simpler molecules. These communities likely gathered near underwater vents and shallow pools some 3 billion years ago, where sulfur remained plentiful and constantly renewed by the rock beneath them. Their chemistry produced hydrogen sulfide as a byproduct, the same compound that gives rotten eggs their smell today, though nothing then had a nose to notice it. Modern life runs mostly on oxygen, but this early life ran on sulfur instead, a fuel drawn from stone rather than from air. A visitor standing at the edge of one of these pools might have smelled something closer to a struck match than to open water. Life, it seems, will use whatever the earth happens to offer. Isotopic signatures in ancient rock hint at active sulfur-cycling organisms. Sulfur comes in several slightly different forms, called isotopes, each carrying the same chemical behavior but a different mass. Certain ancient rocks, some more than 3 billion years old, show unusual ratios between these forms, patterns that ordinary geological processes struggle to explain on their own. Scientists believe such patterns point toward biology, since living organisms tend to favor the lighter isotopes when processing sulfur, leaving a distinctive trace behind in the minerals that form. This does not prove which organisms did the processing or exactly how they lived, and the rock itself stays silent on those details. What it offers instead is a signature, a kind of fingerprint left by chemistry that life alone tends to produce. Reading such a signature means reading a chemical diary, written by creatures too small and too old to leave any other kind of record. The rock remembers what no eye ever saw. Carbon isotope ratios in Archean rocks suggest biological activity was widespread. Carbon, like sulfur, exists in more than one form, and living cells show a clear preference for carbon 12, the lighter and more common kind, over carbon 13, the heavier one. Across many Archean rock formations, from Greenland to South Africa, geologists have found carbon that is measurably lighter than what non-living chemistry alone tends to produce. This pattern turns up again and again in rocks separated by hundreds of millions of years and thousands of miles, suggesting the process behind it was common rather than rare. It does not identify a single organism or trace a single lineage, only a broad signal that something alive was breathing carbon in and out across much of the ancient world. Compared to a single fossil, which tells the story of one creature in one place, this signal speaks for entire ecosystems too small and fragile to otherwise leave a trace. An entire world of life may be hiding inside a number written in stone. Living organisms process carbon isotopes differently than non-living chemical reactions. When a cell builds sugars or proteins, the enzymes doing the work move slightly faster when handling the lighter form of carbon and slightly slower with the heavier one, typically favoring it by only a few parts per thousand. Over countless reactions, this small preference adds up, leaving living tissue enriched in light carbon and leaving the surrounding environment slightly enriched in the heavier form left behind. Chemical reactions that happen without any organism involved rarely show this kind of consistent bias, since they are not shaped by the picky machinery inside a cell. This is why the pattern is treated as a marker of biology, rather than of ordinary geology alone, where a volcanic vent might release carbon in roughly even ratios. A living cell quietly sorts it into lighter and heavier piles across billions of small transactions. The bias is not a signal any organism intended to leave. It is simply what life does to the atoms that pass through it. This isotopic fingerprint is one of the strongest clues to early life. Fossils require exceptional conditions to form and survive for billions of years, since soft, single-celled organisms rarely leave a shape behind for later ages to find. Isotopes, by contrast, survive almost anywhere carbon or sulfur was ever incorporated into rock, which makes them a far more common form of evidence from the Archean than any fossil could be. Scientists weigh this kind of clue carefully, since isotopic patterns can sometimes form through processes unrelated to life, and each site must be checked against known non-biological explanations before it earns any confidence. Even so, the sheer number of sites showing the same biological pattern, spread across continents and hundreds of millions of years, makes coincidence an increasingly difficult case to argue. Unlike a skeleton or a shell, this evidence has no shape at all, only a ratio, quiet and easy to overlook, unless you already know to look for it. Sometimes the clearest proof of life leaves no image behind, only a number. The oldest possible microfossils come from the apex chert in Australia. This rock formation, located in the northwestern part of the continent, dates to roughly 3.5 billion years ago and contains thread-like structures once proposed as the fossilized remains of ancient bacteria. Under the microscope, these structures resemble strands of cells linked end to end, similar in shape to filaments produced by certain microbes alive today. The claim caused excitement when it was first made, since structures this old and this well preserved are exceptionally rare anywhere on Earth. Later study raised doubts, showing that certain non-living mineral processes can produce strikingly similar shapes without any organism involved at all. The debate remains unsettled, and researchers examining the very same slice of rock have reached opposite conclusions from the same evidence. What the apex chert offers, more than certainty, is a reminder of how thin the line can be between the shape of life and the shape of stone. Some questions from this period may simply never be fully answered. Whether these structures are truly fossils remains fiercely debated among scientists. The disagreement sits at the center of Archean research. where the very oldest possible signs of life are also the hardest to confirm beyond doubt. Some researchers point to certain chemical traces within the filaments, arguing that only living cells could have produced them. Others argue that heat, pressure, and mineral-rich fluids acting alone over billions of years can produce shapes that closely mimic biology without ever containing it. Neither position has managed to fully close the argument, and each new generation of instruments sometimes deepens the puzzle rather than settling it. A younger fossil rarely demands this kind of scrutiny, since its origin is usually clear within a single glance. A geologist studying these filaments today must weigh chemistry against geometry and geometry against imagination before reaching even a tentative conclusion. The rock keeps its answer close. Some traces from the deep past may never agree to be fully read. Clearer evidence comes from the Strelley Pool Formation, also in Australia. Located in the same ancient region as the apex chert, it preserves a very different kind of record, built on shape and structure rather than fragile threads. Here the rock holds broad, dome-like forms that once rose gently from a shallow seafloor. Their preservation is unusually good, helped by a type of fine sediment that settled and hardened around them soon after they formed. This has allowed researchers to study the surrounding environment with a confidence that a single ambiguous filament could never offer. A whole field of domes, repeated across a wide stretch of ancient shoreline, is far harder to explain away as coincidence or mineral accident. Where the apex chert leaves a question mark, the Strelley Pool leaves something closer to a signature, faint but consistent across the whole formation. Few places on Earth hold a shoreline this old, still wearing the shape it kept 3 billion years ago. These rocks, about 3.4 billion years old, show layered microbial structures. They sit within a shallow marine setting formed from silica-rich sediment that later hardened into chert and preserved their fine detail. Each layer measures only millimeters thick, yet together they build up into shapes that can be traced by hand across an exposed rock face. Dating these layers precisely required measuring the decay of radioactive elements trapped within surrounding volcanic material, since the sediment itself holds no reliable clock of its own. The resulting age places these structures among the oldest widely accepted evidence of life anywhere on the planet. A rock this old rarely survives at all, let alone with pattern intact, since 3.5 billion years of shifting continents tend to erase such delicate detail. To trace a single layer with a fingertip is to touch a moment when the ocean was barely more than a young and restless film of water. Time here has been unusually gentle. Such structures, called stromatolites, form when microbial mats trap fine sediment. A microbial mat is simply a thin community of microorganisms, growing together in overlapping sheets across a surface, often on the floor of shallow water. As grains of sediment drift down through the water, the sticky surface of the mat catches them and holds them in place. Over time, this trapped material becomes part of the mat itself, and a new layer of living organisms grows across the top of it. The process repeats slowly, one thin layer settling upon another, until a solid structure begins to take shape beneath the water. No single event or organism decides the final form, and the mound grows only through countless quiet repetitions across long stretches of time. A stromatolite is less an object built with intention and more a record of patience made visible in stone. Nothing about its formation requires urgency. Only time, and enough of it, was ever needed. Layer by layer, these mats built low mounds across the shallow seafloor, rising only a little with each new addition. A single mound might grow no more than a few centimeters over an entire human lifetime, which makes its final shape a monument to an almost unimaginable stretch of accumulated days. Some mounds spread wide and flat, while others rose into low domes or branching columns, depending on the strength of currents and the shape of the seafloor beneath them. Fields of these mounds could stretch for considerable distances along ancient coastlines, forming some of the first visible structures ever built by living things on Earth. Nothing about them moved, and nothing about them hunted. Yet they altered the sea floor around them all the same. A coral reef today grows through a similar patience, though built by very different kinds of life entirely. What rose from the Archean seafloor was quiet, slow, and utterly without hurry. The mounds simply grew because growing was all they needed to do. Living stromatolites still grow today in a few salty coastal lagoons, most famously along the shore of Shark Bay in Western Australia. The water there is unusually salty, which keeps away the grazing snails and small creatures that would otherwise disturb the delicate microbial mats before they could harden into structure. Under these rare and sheltered conditions, the same slow process that built Archean mounds continues almost unchanged, layer settling upon layer across the shallow seafloor. Visitors can walk along a boardwalk built above the lagoon and look down at shapes that echo billions of years of unbroken pattern. These living stromatolites grow only a fraction of a millimeter each year, so the largest among them may represent many centuries of quiet accumulation. Almost nowhere else on the modern planet do conditions allow this ancient process to continue so plainly. A shallow lagoon in Western Australia holds, in slow motion, a scene otherwise erased from the rest of the Earth's surface. Cyanobacteria, or a related ancestor, may have built some Archean stromatolites, binding sediment together as they carried out an early form of photosynthesis. These microorganisms use sunlight to produce energy, releasing oxygen as a byproduct of the process, a function that would later reshape the chemistry of the entire planet. Whether the exact organisms living within Archean mats matched modern cyanobacteria precisely remains uncertain, since only structure and chemical trace, and never a preserved cell, has survived from so distant a time. Even so, the resemblance between ancient and modern mat-forming behavior is difficult to dismiss as coincidence. If these early organisms did practice photosynthesis, their mats represent some of the first steps toward an oxygen-rich atmosphere, arriving long before such a change could be measured in the air itself. A humble mat of single-celled life, trapping grains of sand in shallow water, carried consequences reaching every breath taken since. Small beginnings in this world rarely stayed small for long. If so, a primitive form of photosynthesis had already begun. In the shallow waters of the Archean world, microbial mats may have learned to draw energy from sunlight long before the atmosphere carried any trace of oxygen. The earliest chemical signatures suggestive of this process, faint carbon ratios preserved in ancient rock, point to a date near 3.5 billion years ago. This form of photosynthesis need not have resembled the process familiar today, since it likely relied on compounds already dissolved in the water rather than water itself. Its purpose was simple: converting light into usable energy for cells with no other reliable fuel. Where sunlight reached the surface, life may have quietly begun harvesting it, cell by cell, mat by mat. To stand at that shoreline would be to watch nothing stir at all. Yet beneath that stillness, the first machinery the planet ever built for turning light into life was already quietly running. Early photosynthesis likely did not yet produce oxygen as a byproduct. This earliest version of the process converted sunlight into energy without releasing the gas that would later transform the planet's air. Some estimates suggest this quieter form of photosynthesis persisted for several 100 million years, before any oxygen-producing version appeared. The absence of released oxygen was not a failure of the process, but a different chemical pathway entirely, one still used today by certain sulfur bacteria living in oxygen-poor springs and stagnant water. Its consequence at the time was modest, energy for the organism and little else, leaving the surrounding water and sky unchanged. Unlike the oxygen-releasing photosynthesis that would eventually reshape ocean and atmosphere alike, this earlier version left barely a trace on the wider world. A body of water crowded with such organisms might have looked no different from one entirely without life. The chemistry of change was there. It waited, quietly, for a different pathway to arrive. Instead, it may have used hydrogen sulfide, or iron, rather than water as its source of electrons. Where modern plants split water molecules to release oxygen, these early organisms likely stripped electrons from compounds already abundant in the Archean Ocean, compounds far easier to break apart. Hydrogen sulfide, a gas familiar today from the smell of rotten eggs, and dissolved ferrous iron, common throughout the iron-rich seas of this era, both offered accessible sources of the electrons needed to turn sunlight into usable energy. Neither compound matched the energy yield of water, and neither released the same abundant byproduct into the surrounding water. Sulfur particles or rust-colored iron minerals settled instead, drifting quietly to the seafloor rather than rising into water or air. Life, in this early form, worked with whatever chemistry the ocean offered most freely. Nothing about the process demanded the elegance evolution would later achieve. It worked with whatever chemistry lay nearest, and asked for nothing more. True oxygen-producing photosynthesis likely evolved sometime within the Archean, though the exact moment remains beyond reach. This newer version accomplished something none of its predecessors could, splitting water molecules apart and releasing oxygen directly into the surrounding water as a byproduct. Geochemical traces suggest this innovation may have appeared close to 3 billion years ago, carried by an ancestor of modern cyanobacteria. The shift demanded more complex biochemistry than earlier forms, since water resists being broken apart far more than sulfide or iron does. Its consequence, though invisible for millions of years afterward, would eventually alter the chemistry of oceans, rock, and air alike. Where earlier organisms left the world largely unchanged, this new chemistry began quietly producing something the planet had never held in any quantity before. A single cell drifting in shallow water carried, without knowing it, the first working version of a process still running in every leaf today. The old chemistry did not vanish. It merely gave way to something new. Exactly when oxygenic photosynthesis first appeared is still not fully settled, and the record grows more contested, the deeper one looks. Some geochemical signals suggest a date as early as 3.5 billion years ago, while more direct evidence for oxygen's presence does not appear clearly in the rock until closer to 2.7 billion years ago. The gap between these estimates spans hundreds of millions of years, a length of time difficult to hold in mind against any single human life. Part of the difficulty lies in separating early biological signals from later contamination or non-biological chemical processes that can mimic them closely. Fossils can only tell us so much, and the organisms responsible left no shells or bodies capable of preserving such fine detail. Researchers continue narrowing the window, though a single settled date has not yet emerged from the evidence available. The record goes quiet here, exactly where the answer matters most. Time, in this instance, keeps its secret well. Once oxygenic photosynthesis appeared, the oxygen it released reacted almost immediately with iron already dissolved throughout the ocean. Archean seas held enormous quantities of dissolved ferrous iron, delivered steadily by volcanic vents and weathering rock, since no oxygen yet existed to draw it out of solution. The moment free oxygen entered the water, it bonded with that iron to form solid, rust-colored minerals, much the same reaction that forms rust on an iron nail left out in the rain. This process acted like a vast chemical sponge, absorbing newly produced oxygen almost as quickly as it appeared and preventing it from accumulating in the water or escaping into the sky above. For perhaps hundreds of millions of years, this reaction may have delayed any wider change to the atmosphere. No matter how steadily life kept producing oxygen, the ocean, in effect, held the planet's breath before allowing it to escape. Change had already begun. It only waited its turn to surface. This reaction between oxygen and dissolved iron produced layered deposits called banded iron formations, among the most striking rocks preserved from this era. These formations appear as alternating bands of dark, iron-rich mineral and pale silica, sometimes stacked in patterns hundreds of meters thick across ancient seafloors. Places such as the Hamersley region of Western Australia and parts of the Great Lakes in North America preserve some of the finest examples anywhere on Earth. Each band likely reflects a shift in the balance between oxygen production and iron availability, though whether this rhythm followed seasons, years, or far longer cycles remains uncertain. These deposits now supply much of the world's iron ore, mined from rock that formed as a direct record of the ocean's chemistry billions of years ago. To walk along an exposed cliff of banded iron is to walk along a striped diary the ocean once kept of its own transformation. Rust, in this ancient telling, was never a sign of decay. It was the mark of a world learning to breathe. These striped rocks, alternate bands of iron-rich and silica-rich mineral. Similar sequences appear on nearly every continent, tucked into some of the oldest exposed crust on the planet. In the Isua greenstone belt of Greenland, individual bands can be thinner than a fingernail. Yet stacked together, they form cliffs, rising taller than a 10-story building. No single band was laid down quickly, and the exact rhythm behind their formation is still debated among those who study them. What they preserve is not decoration, but chemistry, a frozen record of an ocean's shifting balance between iron and oxygen. Modern seas hold almost none of this dissolved iron, so nothing like these formations is being made today. Run a hand across a polished slice of this rock, and you are touching a boundary between two entirely different oceans, one before oxygen and one after. The stripes do not tell a story of decay, they tell one of exchange. Banded iron formations are among the most reliable records of Archean seas. They form only when dissolved. Iron and free oxygen meet in specific proportions, a condition met almost nowhere on Earth after roughly 1.8 billion years ago. Most Archean examples date between 3.8 and 2.5 billion years, clustering into distinct pulses rather than a steady trickle. Gaps between these pulses may mean oxygen production paused, or simply that iron ran short in certain basins, and geologists still argue over which explanation fits better. What survives functions like a geological instrument, translating invisible chemical shifts into something a person can see and measure today. Tree rings record years, one at a time. These bands record something closer to the breathing pattern of an entire ocean. Standing before an outcrop of banded iron is standing before an instrument reading events no human eye ever witnessed. Nothing needed to watch for the record to be kept. They suggest oxygen appeared in pulses long before filling the atmosphere. Rather than a steady rise, the chemical record hints at bursts of oxygen production separated by long stretches where conditions reverted to iron-rich and oxygen-poor. Some of these pulses appear separated by tens of millions of years, based on gaps between preserved formations across different basins. This unevenness may reflect real changes in how much oxygen early microbes produced, or it may simply reflect how much iron happened to be available to soak it up at a given place and time. Either way, the pattern argues against any sudden switch from one kind of world to another. A modern reader of oxygen levels sees a flat, dependable number on every weather report. An Archean reader would have seen a number that rose, vanished, and rose again over spans longer than entire human civilizations. To read these pulses is to watch a planet rehearsing a change it had not yet learned to keep. For most of the Archean, that oxygen was absorbed as fast as it formed. Photosynthetic microbes had already been releasing oxygen into shallow waters for perhaps hundreds of millions of years, yet almost none of it reached the surface or the air above. Estimates place this balance somewhere between 3 billion and 2.5 billion years ago, a span longer than the time since complex animals first appeared. During this stretch, the ocean acted as both producer and consumer, manufacturing oxygen and quietly using it up in the same breath. Nothing about this equilibrium was fragile, since it simply required more iron than oxygen at any given moment, a condition met almost everywhere in Archean seas. Today, oxygen entering water reacts with almost nothing, and every molecule stays free to circulate or escape. Picture two invisible tides moving through the same water, one building and one erasing, locked together for longer than most rock formations survive. The balance held until the ingredients that maintained it finally ran out. Iron in the ocean acted like a giant sponge for early oxygen. Dissolved iron flowed constantly into Archean seas from cracks in the ocean floor and from rock worn down by ancient rivers, keeping concentrations thousands of times higher than anything found in seawater now. Every trace of oxygen released by early life bonded to that iron almost instantly, converting a gas into solid mineral before it ever had the chance to drift upward. This was not absorption in the way a sponge holds water, but a one-way chemical reaction that locked oxygen into rock for good. As long as fresh iron kept arriving, the ocean had an almost limitless capacity to keep consuming what life produced. A modern ocean holds so little dissolved iron that a similar reaction now barely registers at all. Imagine a fire that never quite catches. Its fuel lit and extinguished in the same instant, over and over, for 100 million years. The flame had already begun. It simply had nowhere yet to spread. Microbial mats likely coated much of the shallow seafloor worldwide. Wherever sunlight reached shallow water across the Archean world, layers of photosynthetic and other microorganisms settled onto the sediment and began to grow across every available surface. Fossil traces from rocks dated to roughly 3.2 billion years ago show these mats spread across shallow lagoons and tidal flats spanning entire coastlines rather than isolated patches. Individually, each mat consisted of organisms too small to see without magnification, yet together they formed a living carpet capable of covering vast stretches of seafloor. Their presence changed how sediment settled, how light penetrated the water, and how oxygen moved between the mat's surface and the water above it. Today, similar mats survive only in a handful of extreme settings, pushed to the margins by animals that graze on anything so exposed and undefended. An Archean shoreline would have looked carpeted edge to edge in living green and gold, unbroken by any mouth that might eat it. Nothing yet needed defending, and nothing yet did the eating. These mats formed thin, resilient films binding sediment grains together. Threads and filaments produced by the microorganisms wove through loose grains of sand and mud, gluing them into place against the pull of tides and currents. A single mat might be no thicker than a few millimeters, yet its binding strength could hold a layer of sediment together long enough for another layer to settle on top of it. Over years and centuries, this layering built up the earliest laminated structures preserved in the rock record, some of which later grew into the domed shapes recognized as stromatolites. None of this required coordination or intention, only the steady growth and regrowth of countless individual organisms doing the same simple task in the same place. A modern beach shifts and rebuilds itself with every tide, unbound by anything living. An Archean shoreline, by contrast, held its shape a little longer, stitched together by something too small to see. The sea floor, it turns out, once needed no rock to remember its own shape. Life at this stage left no shells, bones, or hard parts. Across the Archean, nearly every organism that existed was built entirely from soft tissue, without a single mineral structure to anchor it in the rock. For close to 2 billion years, nothing on Earth grew a shell, a tooth, or a plate of any kind. This was not a failure of biology, but simply timing, since the biochemical machinery for building hard structures had not yet appeared in any lineage. Without hard parts, almost nothing from this immense span of time survived as a body fossil. And what we know comes instead from chemical traces and rare impressions in fine-grained rock. Later, oceans would fill with creatures wearing armor, spines, and shells built to endure for millions of years after death. Here, everything that lived was as fragile as the water that carried it. To picture an Archean sea is to imagine a world entirely without armor, where nothing had yet learned to keep any part of itself past the moment of dying. Everything soft-bodied and microscopic simply dissolved or disappeared after death. When an Archean organism died, its cell walls broke down within hours, and its contents scattered into the surrounding water and sediment. There was no skeleton left behind to slow the process, no armor to hold a shape long enough for burial to preserve it. Bacteria and other microbes recycled the remains almost immediately, drawing the same atoms back into new bodies before any trace could harden into stone. This meant that the ordinary record of Archean life is not a record of bodies at all, but of chemistry left behind by populations too small and too soft to leave anything else. Fossils from this era are the exception rather than the rule, preserved only where conditions happened to freeze a moment of decay before it finished. A human bone can last thousands of years in the right soil. An Archean cell rarely lasted a single season. The story of this world was written and erased in the same breath. Genetic evidence suggests the last common ancestor of most life lived nearby this time. By comparing the genes shared across every branch of life today, from bacteria to whales, biologists can trace backward toward a single ancestral population from which all of it descended. That population appears to have existed somewhere between 3.5 and 3.8 billion years ago, placing it firmly within the Archean world of grey skies and green oceans. This ancestor was not one particular organism, but a group, likely a loose community of similar microbes trading genetic material freely among themselves. Its existence explains why the basic machinery of life, the way cells read DNA and build proteins, is nearly identical in every living thing today. Every plant, animal, and fungus alive now carries a faint echo of chemistry first assembled in that Archean population. Every living thing today still speaks a dialect of that same first chemical language. That language was spoken nowhere but in the ancient, unwitnessed dark. Horizontal gene transfer, sharing genes without reproduction, may have been common. Rather than passing genetic material only from parent to offspring, Early microbes appear to have exchanged fragments of DNA directly with neighboring cells, regardless of lineage. A gene that proved useful, perhaps one that helped tolerate heat or process a particular mineral, could spread sideways through a community in a matter of generations, moving between organisms that were not related at all. This kind of sharing left genetic fingerprints that scientists can still detect, scattered unpredictably across the family tree of early life. It meant that evolution in the Archean did not always move in the tidy, branching pattern we imagine today, but sometimes moved sideways instead, gene by gene, cell by cell. In a modern forest, a squirrel cannot borrow a trait from a nearby oak. In this ancient ocean, the equivalent might have happened routinely, without ceremony or consequence. Life then shared its secrets more freely than it does now. This blurred the boundaries between early species in ways rare today. When genetic material moves easily between unrelated organisms, the very idea of a fixed species becomes difficult to apply, since the line between one population and another can shift with every exchange. Early microbial communities likely formed a continuum rather than a set of distinct branches, each population borrowing and lending traits until the differences between them grew difficult to trace. Modern classification depends on lineages that stay mostly separate, reproducing within themselves and diverging slowly over time. The Archean world offered no such tidy separation, only a shifting mesh of related and unrelated organisms trading pieces of themselves back and forth. Scientists studying this period often describe early life less as a tree and more as a web, its threads crossing in every direction. Sorting Archean microbes into strict species imposes an order the organisms themselves never respected. The boundaries we rely on today simply had not been invented yet. No predator-prey relationships likely existed among these simple, single-celled organisms. Predation, as we understand it, requires one organism to actively pursue, capture, and consume another. A set of behaviors that depends on speed, sensing, and coordination that early microbial life had not yet developed. Archean organisms instead competed indirectly, drawing on the same limited pools of minerals and chemical energy without ever encountering one another as threats. A cell might starve because a neighboring mat consumed the available nutrients first, but it was never hunted, chased, or eaten in any active sense. This absence removed an entire category of pressure that shapes life today. The pressure to flee, to hide, or to grow defenses against another creature's appetite. Modern oceans are layered with hunters and the hunted, an arrangement so old it feels inevitable. In the Archean, no organism yet had anything to fear from another's hunger. Survival was a matter of chemistry finding its footing, not one body escaping another. Archean life's entire drama played out in chemistry, not motion or behavior. Where later life would come to depend on movement, sensing, and complex behavior to survive, Archean organisms achieved everything they needed through reactions occurring quietly within and around their cells. Growth, competition, and even the earliest forms of cooperation unfolded as shifts in chemical gradients rather than as visible actions between bodies. An organism did not chase resources. It simply existed in a place where the right molecules happened to be available, or it did not survive to leave descendants. This made the Archean world profoundly still, by any standard we would recognize today, even as its chemistry churned with more activity than most modern ecosystems ever produce. What looks like emptiness in the fossil record was in fact a world working constantly beneath the surface, unseen and unhurried. Nothing in that world ever needed to notice anything else in order to survive. The story of early life was told entirely in molecules and never once in movement. The pace of change across this era was almost unimaginably slow. Across the middle stretches of the Archean, a single lineage of microbes might persist, largely unaltered, for 400 million years or more. This is not stagnation in the way we might imagine boredom or failure, but a kind of chemical contentment, a form so well suited to its narrow niche that nothing pushed it to become anything else. Evolution here was not idle, only patient, tuned to a world where the same handful of reactions could sustain life indefinitely without needing improvement. Set against a human life in which a single decade can remake a person's habits, body, and mind, 400 million years of near sameness is difficult to hold in the imagination at all. Picture a single quiet pond, its waters the same shade of green for longer than mountain ranges have stood and fallen elsewhere on the planet. Change was always present in the Archean. It simply moved on a clock that owed nothing to human patience. Entire epochs passed with life remaining chemically similar, generation after generation. Geologists divide the Archean into 4 long eras, each one lasting longer than the whole of time since the extinction of the dinosaurs. And within many of these divisions, the microbial record shows almost no meaningful shift. The same isotopic signatures, the same layered mats, the same simple metabolisms appear near the top of a rock sequence as near its base, sometimes across tens of millions of years of sediment. This continuity likely reflects a world where the available chemistry itself changed little, leaving organisms with no new opportunities to exploit and no new pressures forcing adaptation. Human species turn over within centuries, but an Archean lineage might outlast the rise and wearing away of an entire mountain range without altering its basic chemistry at all. Reading those rock layers means reading the same passage copied out across 100 million years, patient and unchanging. Repetition here was not failure. It was simply what worked. Toward the Archean's later half, continental crust grew more rapidly. Roughly 3 billion years ago, after more than 1 billion years of gradual, uneven crust formation, the rate at which new continental material formed increased noticeably, according to isotopic evidence preserved in ancient rock. Geologists estimate that a substantial portion of all continental crust that exists today, perhaps as much as half by some calculations, had already formed by the end of this period. The reasons for this acceleration remain debated, tied perhaps to changes deep within the mantle, or to a shift in how heat escaped the planet's interior. Whatever the cause, the effect was a planet steadily gaining solid ground, its scattered islands and shallow shelves slowly thickening into something closer to the continents recognizable today. A modern coastline, with its cliffs and river deltas, owes its very existence to crust laid down in these slow-building final chapters of the Archean. The Earth was assembling its skeleton long before anything stood on it to notice. Granite, common in modern continents, became more abundant during this span. This pale, coarse-grained rock, familiar today as kitchen countertops and quarried building stone, requires repeated melting and slow cooling deep within continental crust to form, a process that depends on crust already being thick enough to sustain it. Its growing abundance across the later Archean suggests that continental crust had, by then, thickened enough in places to melt and remelt itself, refining rock the way a forge refines metal through repeated heating. Early Archean crust had been dominated by darker, denser rocks better suited to thin, young crust still finding its footing. The shift toward granite marks a planet whose land masses were no longer simply floating fragments, but were beginning to behave like the stable, layered continents of later ages. Granite countertops, cut and polished in ordinary kitchens today, are quiet fragments of that same process, sped along by 3 billion years of further geological refinement. Stone, in this sense, remembers what soil and ocean cannot. Some researchers propose a supercontinent called Valbora existed by this time. The name combines two of the oldest surviving pieces of continental crust on Earth, the Cap Val Craton in southern Africa and the Pilbara Craton in Western Australia, both dated to roughly 3.5 billion years old. If Valbora existed, it would represent the first assembly of separate crustal fragments into something resembling a single, unified landmass, long before the more familiar supercontinents of later geological history. Such an assembly would have been small by later standards, perhaps no larger than a present-day continent, surrounded by vast stretches of open ocean on every side. Its existence would suggest that plate movement, however slow, was already capable of drawing distant fragments of crust together rather than only spreading them apart. A single gathered landmass, adrift on a young planet's restless surface, is a striking image for a world with no coastlines anyone would recognize today. Valbora, if real, would be the Earth's first attempt at wholeness. Evidence for Valbora comes from matching rock sequences across separate continents today. Geologists studying the Cap Val Craton in Africa and the Pilbara Craton in Australia have found strikingly similar layers of ancient sediment and volcanic rock, laid down in matching order and dated to matching ages, despite the two regions now sitting thousands of miles apart. Such alignment is difficult to explain, unless the two cratons once sat side by side, receiving the same volcanic ashfalls and the same shifting seas before drifting apart over billions of years. It is as though two pages torn from the same book turned up on opposite sides of the world, their text lining up when placed back together. This kind of matching, used since the early study of continental drift, remains one of the most persuasive tools available for reconstructing landmasses that vanished long before any map could record them. The rocks themselves become witnesses, carrying testimony no observer was ever present to write down. Whether Valbora truly existed as one landmass remains an open question. Some geologists argue that the matching rock sequences could result from separate cratons experiencing similar global conditions independently, rather than from physical proximity on a single continent. Others maintain that the alignment is too precise, too consistent across too many rock types, to be explained by coincidence alone. The debate remains active because so little Archean crust has survived intact, worn away, or buried by billions of years of later geological activity, leaving only scattered fragments from which to reconstruct an entire vanished world. A modern mapmaker works from satellite images and ground surveys, while an Archean geologist works only from a handful of surviving stones and the patient comparison of their mineral fingerprints. The uncertainty itself feels appropriate to an era this old, more shadow than photograph, more suggestion than record. Valbora may have been real, or it may simply be the shape scientists have drawn across an absence. Either way, the question outlives the answer. By around 2.5 billion years ago, oxygen levels began rising sharply. For most of the Archean, the atmosphere had held only faint traces of it. A gas produced but never allowed to accumulate, absorbed as quickly as it formed. Now, across a span of perhaps 100 million years, its concentration climbed from a fraction of a percent toward levels a modern lung could almost recognize. The rise was not smooth. It came in pulses, some rock layers showing sudden increases, others retreating soon after, a rhythm no one has fully explained. Its consequence was immense. Iron dissolved in ancient seas began to rust and settle, painting ocean floors in bands of red and grey that still lie exposed on several continents today. Where the early ocean had been clear of such colour, it now wore the tint of slow oxidation, the way an old nail reddens left out in rain. To stand at that shoreline would have been to watch a world quietly changing its chemistry underfoot. The air was learning to hold its breath no longer. This shift marks the traditional boundary between the Archean and Proterozoic eons. Geologists needed some way to divide a history spanning billions of years, and the change in atmospheric chemistry offered the clearest marker they had found. The boundary is set at 2.5 billion years ago, a date drawn not from any single dramatic event, but from accumulated evidence in rusted rock, sulfur chemistry, and shifting mineral deposits found across the globe. Nothing marked that moment for the planet itself. No sunrise announced a new eon. The division exists only in human record-keeping, a line drawn across a continuum to make an unmanageable span of time speak in chapters. Its usefulness lies in organization rather than truth, a convenience that helps scientists compare 1 billion-year stretch against another. Where a human calendar marks a new year at midnight, Earth's calendar was written afterward, by people sorting through stone long after the moment had passed. The Archean did not know it was ending. It simply continued until the rocks it left behind told a different story than the rocks that came after. The change is now called the Great Oxidation Event by geologists. The name suggests suddenness, though the event itself unfolded across hundreds of millions of years. Slow by any human measure, but abrupt within the vast patience of the Archean. It reshaped nearly every chemical system on the planet's surface, from the minerals forming in shallow seas to the gases escaping through volcanic vents. Before it, most rocks recorded a world starved of oxygen. After it, entire new classes of minerals began appearing in the geological record, formed only in oxygen's presence. Scientists still debate exactly how quickly the transformation took hold in different regions, since some ancient basins show oxygen appearing far earlier than others nearby. What is certain is the result: a planet whose air and rock chemistry were permanently altered, never to return to their earlier state. Nothing since has undone it. The label given to this shift is modern, chosen long after the event itself. But the rocks that preserve it are exactly as old as the world that produced them. Cyanobacteria are thought to have driven this slow, world-altering transformation. These single-celled organisms had been converting sunlight into energy for perhaps 1 billion years, before oxygen ever accumulated in the air, releasing the gas as a simple byproduct of their metabolism. For most of that time, the ocean itself absorbed what they produced, binding oxygen into iron and rock rather than releasing it upward. Only once those chemical sinks filled, saturated after ages of steady output, could the surplus finally escape into the atmosphere above. To trace the origin of breathable air back to something this small is to realize how disproportionate cause and consequence can be across deep time. No organism intended to reshape a planet. They simply lived generation after generation, until their combined output overwhelmed every buffer the early Earth had to offer. The transformation belonged to no single moment and no single creature, only to the patient arithmetic of trillions of lives repeated across hundreds of millions of years. Photosynthesis had already been quietly rewriting the world long before geology noticed. Oxygen buildup would eventually poison many organisms adapted to its absence. For nearly 2 billion years, life on Earth had evolved entirely within oxygen-free conditions. And to many of these organisms, the new gas was not a gift, but a toxin, capable of damaging their basic cellular chemistry. As oxygen spread through the oceans and then the air, Populations of these older organisms collapsed across wide stretches of the planet, retreating into environments the gas could not reach. Some scientists describe this shift as one of the earliest mass extinctions in Earth's history, though it left no bones and no shells, only a change in which chemical signatures appear in the rock. Survivors persisted in mud layers, deep sediments, and hot springs, places oxygen struggled to penetrate, and their descendants still live in exactly such refuges today. Where the surface of the planet was transformed, hidden pockets remained unchanged, sheltering the old chemistry of an earlier Earth. The end of one world, in this case, was simply the retreat of an older one into shadow. That transition, however, unfolds fully only after the Archean's official close. The rise of oxygen did not finish neatly at 2.5 billion years ago. It continued for another 2 to 300 million years, deep into the following eon, before atmospheric levels stabilized into something resembling the balance we know now. Geologists therefore treat the boundary as a convenient marker rather than a true ending, a line drawn through the middle of an ongoing process rather than after its completion. Sediment layers from this later period still show oxygen advancing unevenly, region by region, arriving in some shallow seas centuries before it reached others nearby. A slow tide crossing an uneven shoreline captures the pace better than any single date could. Some inlets filling long before others felt the same rising water. That unevenness is written directly into rocks from both eons. A reminder that the boundaries scientists draw rarely match the boundaries nature actually kept. The Archean ended, by definition, long before the transformation it began had finished playing out. The Archean's rocks preserve nearly a third of Earth's entire history. The eon itself spanned close to 1.5 billion years, from roughly 4 billion to 2.5 billion years ago, out of a planet only 4.6 billion years old in total. Very little of that record survives intact. Heat, pressure, and billions of years of geological turnover have destroyed or transformed most of what once existed, leaving only a scattering of ancient cratons in Africa, Australia, Canada, and elsewhere to speak for the entire eon. What remains is disproportionately valuable, precisely because so little of it remains at all. Each surviving outcrop carrying evidence found nowhere else on the planet's surface. A modern geologist reading these rocks works with fragments the way a historian might work with a handful of surviving pages from an otherwise lost library. The eon shaped the air, the oceans, and the continents that followed it, though it left behind only enough stone to hint at how. Nearly a third of Earth's story survives in scraps, and those scraps are still being read. Cratons formed in this eon still anchor several modern continents today. These are the oldest, most stable cores of continental crust, thick slabs of rock that have survived every collision and rifting event since their formation. The Karpfel Craton beneath southern Africa and the Pilbara Craton in Western Australia both trace back more than 3 billion years, largely unmoved, while entire oceans opened and closed around them. Not every craton has stayed put, and some have been buried under younger rocks so deep that only careful drilling reveals their presence below. Continents built later attach themselves to these old cores, the way a settlement grows outward from its original foundation, expanding but never quite replacing what was there first. Modern mountain ranges rise nearby. Modern rivers cut across their edges, yet the cratons themselves remain essentially unchanged underneath it all. Beneath a Perth suburb or a village in the South African Highveld, that old Archean rock continues to hold its place. The ground people call solid was old before anything stood on it to notice. Almost everything we know of this world comes from a handful of ancient stones. No continents from this eon survive whole. No fossils of soft creatures remain, and no direct sample of Archean air has ever been recovered. What exists instead are isolated outcrops, isotope ratios locked into crystal structures, and chemical traces preserved in layered rock that formed on ancient seafloors. From these scattered clues, researchers reconstruct an entire planet, its ocean chemistry, its air, its early life, working forward from evidence that could fit inside a single museum room. Much of what feels certain about this eon is, in truth, a careful best estimate built from very thin material. Newer techniques occasionally overturn old conclusions, and questions once considered settled sometimes reopen when a fresh outcrop is found. The Archean will likely never be known the way more recent eons are known, in detail and with confidence. What is known came from stones that happened against long odds to survive. The rest of that ancient world stayed exactly where the story leaves it now, unrecorded and at rest. And so we drift to the end of our quiet journey through the Archean, that first long green oceaned age of the world. From the 21-hour day that turned beneath the dimmer sun, to the low mounds that microbial mats built layer by layer across the shallow seafloor, to the striped rocks that still hold their bands of iron and silica. After 4 billion years, this was a world built slowly, from almost nothing, by almost no one. What this world teaches is not certainty, but patience. So little survives from the Archean that everything we know rests on a handful of stones, and yet those stones are enough to sketch an entire planet, breathing, cooling, and beginning to live. The lesson is not that we know this world completely. It is that a few honest fragments, read carefully, can hold the shape of billions of years. Imagine standing on a craton of new grey rock, while a green ocean laps quietly against its edge, the whole scene lit by a sun that gives less warmth than the one you know. Imagine the shortened day sliding past overhead, the sky darkening a little sooner than you expect, the hours themselves unfamiliar. Imagine a mat of microbes thickening on the seafloor beneath you, building itself upward one invisible layer at a time, with no memory of what it is doing and no need for one. This is the comfort of science told slowly. The world is stranger, richer, and more interconnected than we can ever fully see. And the Archean is proof that even the barest evidence, gathered patiently, can return an entire lost world to us. If you enjoy these quiet journeys into the deep past, feel free to like and subscribe or share a thought in the comments below. It helps others find their way here too, one sleepy soul at a time. But for now, there is nothing more you need to do. You can allow the story of the Archean to fade like the last light of day, leaving only calmness behind. If sleep comes, let it carry you gently. If you are still awake, you are welcome to stay, to listen again, or to let the next video continue your voyage into the quiet wonders of the deep past. Rest well, and remember, somewhere beneath an ocean that no longer exists, on rock that has long since worn away, the first mats of living things went on building themselves, patiently, in the dark, long before there was anyone to notice, and long before there was any reason to hurry. Good night.